Thank you. Okay, this is LJK labeling of direct products of complete graphs. So let me introduce what is LJK labeling. So if you have a graph, let's assume that J is at least K, then an LJK labeling of G is a function from the vertex set of the graph to the non-negative integers actually. And where if two vertices are of distance 1, means if they are adjacent, then their labels are at least J different. And if their distance is 2, then their labelings are at least K different. Okay, in this case, we call the span of F is the maximum difference between labels. So that's really the maximum value of F minus minimum value of F. And usually people put the minimum value to be 0. So you really find, so span is really the maximum value of F. And then we denote that one with the notation lambda JK. So lambda JKG. So actually the proper vertex coloring is L10 coloring, we can say. But here for LJK coloring, usually people are very interested with the case where J is non-negative also. This problem came from frequency assignment. So you have transmitters and you assign frequencies. If two transmitters are very close, then to avoid the interference between them, they want to put very different frequencies. And if they are moderately close, then they want to put moderately different frequencies. So Hale placed this problem in graph theoretic context. So if he represented each transmitters by vertices by a vertex of a graph. And if two transmitters are very close, then he put edges in between them. And if they are moderately close, then somehow he put them into the vertices of distance 2. And Grigg and Yeo proposed this problem, lambda 1, 2 especially, not just lambda JK. And actually people usually worked with lambda 2, 1 or lambda 3, 1. And there are results about passes, cycles, and trees. And also Grigg and Yeo proved that lambda 2, 1G is equals to delta squared plus twice of delta, where delta is the maximum degree of the graph. And they conjectured that this upper bound can go down to delta squared. But the conjecture is still open. So these are the results when you have a pass or cycle or tree. And let me introduce product of graphs. When you have two graphs, G and H, their Cartesian products are defined as follows. So their vertex set is the set of ordered pair of vertices of G and vertices of H. And if x, y, and x prime, y primes are adjacent, if x is same with x prime and y primes are connected in their original graph, or the other way, the direct product of G and H has the same vertex set with Cartesian product of G and H. And when you have two vertices, x, y, and x prime, y prime, they are adjacent if both x and x primes are adjacent in their original graph, and y and y primes are adjacent in their original graph. So if we draw their picture, say if we have G and H, and two vertices x, x prime, y, y prime, then if they are connected and they are connected, then direct product looks like this, and Cartesian product looks like this. So actually,
Cartesian product is.
Oh, I'm sorry. Cartesian product looks like this, and direct product looks like this. So actually, they put that shape from these pictures. Okay, George et al. Found the lambda jk of km, Cartesian product of km and kn. Those are complete graph of order km and kn. And Whittlesey et al. Investigated those. So actually, I told that there are results about the path cycle and trees. And if you have a complete graph, it's easy to find the lambda of complete graph. And there are also results about the product of these graphs, two of these graphs. So they are all about those results. But still, they all talk about product of two graphs, not multiple of them. Okay, and this is the first result about several graphs, several cycles. This is the results concretely, which I told before. Okay. And let's look at direct product of graphs. When you have direct product of complete graphs, which is the main topic of this talk. So when you have two direct product of two complete graphs, if both complete graph has at least three vertices, then the result looks like, looks like this in uppercase. If one of them is at least 2, one of them is case 2, then the result looks like this. Okay, especially in this case, when I'm sorry, let me talk one more thing. When you have complete graphs, direct product of complete graphs, so say you have K3 times K2, then anything is missing? If two vertices have both coordinate different, then they are adjacent. Otherwise, okay, sorry. Let's have K3 times K3. Otherwise, they are of distance 2. So, how can I? If you want, then you come. Sorry, you come here and come back there. So all the vertices are either adjacent or of distance 2. So they should be at least k different to their labels. So for this kind of graph, we can assume that k is 1, actually. And then only the distance, only the ratio of j over k matters. So here we did not do that, but from now on, actually, we are going to do that after this.
So you're assuming the K is
K is 1.
positive. For instance.
Yeah, yeah.
If K is general, then
If K is 0, it's like just coloring. So when J is at most 2, this is actually the possible optimal value, because every vertex must have label at least different from, every vertex must have different labels. Here K is 1, and any vertex has distance at most 2, so then their labels must be different, at least K. That means, in this case, their labels must be different. Well, in this context, maybe we can say that every vertex, any two vertices, at least K different. So then the minimum possible span is the number of vertices minus 1 times K, because it starts from 0. Okay. When J over K is bigger than 2, we have this much extra. Where they came? So you know the shape, the edges. So let's put 0, K, 2K. And this one must be different to at least K with this one and that one. So you put just like at least J much different. So K plus J. And 2K plus J, 3K plus J. Again, this one should be at least J different. So 2K plus 2J, and 3K plus 2J, and 4K plus 2J. Then, actually I should have changed this one. This one is Km times Km. And we can say that M is at least N. Then whenever your N increases, you have this much increase. And before that, if J over K is at most 2, you could have 0K, 2K, and 3K here, because they must be different. And 4K, 5K, 6, that way. So instead of increasing K from here, you increase the J minus K. So optimal 1 plus 3K minus K, the other way, sorry. K plus J minus 3K, this much you increased here. And you do that whenever your N goes up. So in this way, so that's the extra K. Okay, when your N is 2, this is one way you can do it. So you consider up to here, like this. Or in this particular case, because there are only 2 vertices in this line, this distance is not 2 in this case. It's actually 3, probably. So like 1, 2, 3, that way. So there is no restriction in between them. So then they considered this labeling 2K and same one 0K, 2K. And they chose the minimum depending on M or K. M or, okay, depending on M in this case. Yes?
Yeah. So how, I mean, that shows the upper bound of.
Yeah, actually it's upper bound.
Yeah, is it very hard to put the lower bound?
Lower bound, they considered he put. Okay, so when I think I probably made a mistake there. J over K is at least 2 rather than less than 2. In that case, we achieved the minimum possible upper bound. So what they did is they put F0 up to Fmn minus 1 in this increasing order, and they considered some subsequence which is J, and most J restricted subsequences. And then they showed that if there are so J restricted subsequence means subsequences where their difference is at least J, something like that. And if there are 2 consecutive J-restricted subsequences, they found that there is some gap in between these. Not exactly consecutive, but 2 different ones have this much gaps. And then because of that gap, there should be at least this much difference. So that proves that this is the lower bound. Okay, when n is 2, they did the same job. Hawk and Ja in 2008 showed the result of direct product of multiple complete graphs. So direct product of, R complete graphs, and they put their orders n0 up to ni minus 1, and they assumed that those ni's are non-increasing. And they also distinguish 2 cases when all of them are at least 3, or at least one of them is true. So again, they show that if, actually K is 1, but if J is at most these numbers, then you can achieve the minimum possible span. They just talked about this case. They didn't talk about anything about when J over K is bigger. Okay. And when one of them is K2, then they show that this upper bound is possible. Okay, they disposed in this way. So let me put each coordinate to be U0 up to Ui minus 1. There are R coordinates. And depending on this last coordinate, you distinguish layers. Actually, they didn't do that, but I put in this way by looking at their Okay. Thank you. By looking at their labels, I put the labels in this way. So they just put from 0, 1, 2, 3, 4, and then turn around this one. So this rectangle shows the labels when U2 is 0, the zeroth layer, let me call. And then in this case, N0 is 5. So this is the case when U0 is 0 and U0 is 1 in this way. And 1 is 4. So this is the line when U1 is 0 and U1 is 2 in this way. So this is really the example of K5, K4, and K3. And as your U0 increases, your label goes up. And here, at the end, you turn in this way and go with that one, and turn that one, and start at the same place in this upper layer and change the direction that way. So if you remember, he showed the labeling for this case, N0 and R minus 3 plus 1. So especially here, R is 3, so J is just N0 plus 1. Okay, if you just look at this, the smallest label of this upper layer, that's 20, then if the labels are J, then this L can be label of any vertex. But if L is J minus 1, then L should be the labels of vertices which is not adjacent with the vertex of this label 20. And for this vertex, the vertices which are not adjacent with this vertex is whole rectangle where your U2 is the same, or this line where your U0 is the same, not that one, there, your U0 is the same, or U1 is the same. So the vertices which are not different with this one, U0, U1, U2, are the labels where you share the same U0 or share this one or share the third coordinate. Anyway, the vertices which shares at least one coordinate with this one. So especially when J is N0 plus 1, then that one is N0. Then the labels whose this difference from 20 is at least N0 should lie in this place, this line, or this rectangle. So he put in this way. So in this case, that's really from 15 to 19. So they are all in this line. So there is no problem with 20 with them. And by the same token, everything is okay. Okay, if your R is 4, you can dispose in this way. The last two coordinates, 0, 0, 1, 0, 2, 0, in this way. And then for the layers where U3 is 1, then the smallest label is 60. And then in this case, it should be N0, N1 plus 1. So then this 60 minus L is almost N0, N1. They can be all in this rectangle. So from 60, the labels which are different at most to N0, N1, N0 times N1, that's 20. So from 40 to 59, all stay here. So, and they share the third coordinate with this 60. So then there is no problem. But what I considered is here. Actually, if we put 20 not here, down here, then rather than from 15, from 14, you can put the labels which has some trouble with 20. So we can increase the bound of this by putting that way. So rather than 1, it's 2. So we found some possibility of that. And for simplest thing, actually we did like a, okay. We didn't change the direction. Actually, with this one, JAWS result still works. And we put 20 here, then only this one matters. So 14 is also fine. So in that case, we could increase this boundary. For this one also, if you put 60 here, and you can probably increase the boundary with these numbers, and probably one more even. Okay, this about circular coloring we can forget. So we disposed in this way. Just to go through this direction, with this way also JAWS results work. And then here we change the direction when we go to the upper layer when your last coordinate changes. So then here is 20. So now from 14 it's okay. So only here when you go to the upper layer, you change your direction and follow the same directions. And here again, you change it. You start from here and then change your directions. In this case, you are 60. Okay, you've just follow the direction 19 and 20 in that way. And when your last coordinate changes, you start from here and change your direction. And from 60 now, not just this rectangle, this line is okay, and 34 is okay also. So by changing these directions, we could increase the boundary, increase the range for this optimal labeling. So now your J is almost A, and A is not just this JAWS boundary, but you can add this much. And these are just the concrete expression according to this labeling. And also we said if J is bigger than A, then we can find this upper bound. So here we have some extra terms. This is very similar to the ones with two direct product of two complete graphs. So whenever your last coordinate changes, you have some extra ones here. Okay, this is the case where J is bigger than A. So all this matters with this value. So you added J, 13 plus J rather than 20. And then you just follow that. And again, when you get here, you add this plus J here. Okay, and similarly with them, with the result of product of two graphs. So if the last one is K2, then we can also consider this same labeling of two layers. And we just chose minimum of these two methods. Okay, especially when you have K2, if G is bipartite, then G times K2 is isomorphic to twice of G. So then if we have at least two of K2, then they are isomorphic to these ones. So then you can really have a labeling of just one of them and then extend that. Okay. And we want to look at if our upper bound is optimal or not. So of course, this is the case where J is bigger than A. So let me introduce some notations. Let me say something to be whole, if that's the number which is less than lambda, but it's not a label of any vertex. And H, big H denotes the set of wholes. And let me call this one to be J neighbor. Actually, this is down neighbor. So it's J neighbor of L means some I which is less than L, but whose difference is n minus J minus 1. So actually, this one should be denoted by like a L down, N down, L, something like that. But for convenience, let me just denote in this way. And among them, the ones which stays in Y's label is called Y's layer is called NYL. And the upper J neighbor is the labels which are bigger than L, but it's also within J minus 1 distance from L. So in this case, let me write down this NUL. Okay, for the case when R is 3, A was 7, A was actually N0 plus 2, and in this case it's 7. So let's consider the next number. Is this optimal? Okay. Actually, the answer is this is not optimal because J is rather small. And if J is bigger enough, then this is optimal. So in this case, the answer is like that. So then the answer is 2. And let's try to find out labels. So we say X to be the minimum of okay, I used the G instead of F here. U and 1. Some neighbors, U0, U1, to be X. And the first case is X is 20. That means from 1 to 19, from 0 to 19 are all on the basement, all in the basement. So then, when you consider this upper label, so here is up to 19, and here is the smallest number 20, and then N1 of 20 is from 13 to 19. I'm sorry, N020. And N020 is from 14 to 19. And their intersection is 6 numbers, which is bigger than 5. So they cannot stay in one line. So that means they should really, if 20 is here, then they should be really here. Somewhere. They cannot stay in one line, just here or that one. But also 21 should share at least 6 elements here. So then 21 cannot be here. And 21, if it survives, then it should go upper layer even. And then 22. Still share 5 elements with this 20 or 21, the neighbors. So then, say if none of them are wholes, then 20 and 21 is here, then actually from 15 to 19 should be here, and 14 is here, and because 20 is here, 13 should be here. But 22 also have this one within its as their neighbors. So then 20 should be somewhere here or somewhere here. If it contains at least 2 elements in this line, then they should stay here. And then by the same token, 23, 4, 5, they should all stay in these 2 lines. And then first case is if at least one of these stay here even. Okay, at least one of them stay there and one of them stay there. Then you have 2 elements in this line and 2 elements here in this line. Then 26, that contains these 2 elements as its neighbors and 2 elements as its neighbors. So 26 also stay in this line or this line. And by the same token, 27, 8, 9, 30, up to 30, they should all stay here. But that's too many. So it's a contradiction. So that means 22 to 25 all stay in one line, in this layer or in this layer. So let's assume that 22 to 25 stays here. Stay here. And then you consider 26. But then, okay. Okay, if 20, okay, then 23 to 25, they fill up this line. 22, 3, 24, 25. And then your 26, if it stays in this layer, it should stay here. Otherwise, it should stay here. But then 27, again, even containing 26, it should stay here and here. So 26 can stay here or somewhere here. If it stays here, then 27 contain these whole lines. So then 27 should stay here. And then by the same token, as your new element goes up, your upper neighbors goes up. So some more elements should stay here, or they all stay here downstairs. So in this way, you also have too many elements for this line. So then your elements should stay here. So rather than 33, let me change the slice. So if they all stay here, it's until 40. Yeah, it's up to 40. Because it's starting from 20 and 21 is here. So then the first element has lower neighbors 7 many lower neighbors, and 42 have 6 many neighbors. They are all in common. So then if 41 is here, then their neighbors all stay here. But 42 also should be here in that case. So that's a problem. So at least one of these should be a whole. So this is actually the optimal labeling. 20 goes up here. And then 42 is a whole.
What's the empty?
Anything can be done, kind of. So for 41, the neighbors are here, the lower neighbors. And for 43, the lower neighbors are all in this line. And up to 46, 46 have at least 2 elements here, so they should stay in this line. But others can go anywhere. So actually what matters is in one layer, the beginning ones matters because of their lower neighbors. And if at least one of them goes up, then their upper neighbors matters. So we found some algorithm. So let me introduce some notations. So let me call SI to be the story layer, the same thing. So the last element is I. And then Li denotes the maximum possible label in Si. And Mi is maximum size of this kind of upper neighbor of some elements. Okay, this should be changed. The exported must come earlier. So if some element is in between, sorry, no. Okay. So here your L0 is 19, and L1 is like a 40 or 39 something. And 21 is in between this one, but it goes to the upper layer, then we say 21 is exported. And MI is the maximum possible size of upper neighbor of some exported elements. So if 21 is here, then that's the possible size. That's called M1. Okay. So the algorithm. You initialize I to be 0. So actually, in the first layer, you put everything to be 0. There is no export here when you start. There is no hole. And NK prime denotes the maximum size of a line. NK prime is like this. Maximum number of labels for vertices. So, for example, if these are all taken and there is some more element here, now it's, say, if 25 is exported, then your neighbors can be only here, so then their size changes. This was 5, still 5, but here is 3 rather than 4. So anyway, and step 1, you increase your I by 1, and from, this should be Li. From Li plus 1 in the upper layer, you consider beginning labels, and if they all fit in one line in this kind of shape, that's fine, but otherwise you make some holes or export. And then this is number of exported ones from ith layer. There should be at most this one. And if there is some export, then consider its neighbors. And again, considering your adjusted MI, you make some of them whole or export some of them. And just repeat as much as you need. Okay, so for example, okay, let's consider this case. In the ith layer, the first element has lower neighbors size j minus 1. So here, in this case, we consider 20. Then its lower neighbors, and 020 has size 7. No, 7, that's j minus 1. And then N021 has 6 in this way. If some element has more than I minus 1, then they should be a whole or exported because their neighbors can fit into just mi minus 1. Okay, so these many sorry. No, I'm sorry. If something is exported, they must have upper neighbors of size M0. So if their neighbors are even bigger than that one, they cannot even be exported. So they must be wholes. And then from the next one, if their neighbors is of size mi-1, they can be exported. And because EI, many of them exported, so up to here they can be exported. Of course, you can export to something bigger, but this one is more convenient because their upper neighbor goes up to small numbers. And then some of them you again make a whole, because if their neighbor has size n+2, then the next one should have size n+1. This is the case where it's 7 and 6. Then one of them should go away. So we can say up to here, it goes away. So then your number of holes looks like this upper one and that one. And if you consider this one, this is from n+2 to j-1. So the size is totally j-n-2. That's j-a. And here you just subtracted your exported ones. But if EI is bigger, then you should consider its upper J neighbors. And then you call them B and consider its size B. And this is not N, this should be MI, sorry. So if it's bigger than MI, then the remainder should be exported or becomes whole again. And then, so then this slide also should be changed, I'm sorry. So in this case, when R is 3, H is J minus N minus 2 plus maximum so plus in the next layer minus 2. And we're going to consider if this one is at least twice of J minus A or not. And if J is means if this is at least 0, no, not here first. In this case, if we add E1, that should be also at least 0. So then this addition is H is bigger than J minus A if and only if this one. Let me just write down. So. And this is like that one is true. J minus A. If and only, and this is a case when J is at least 10. Because these are all 8, 8, and 5, 1. So actually, for the last, when one layer there is J, here is just 2, but you have J, J, J as 3 times. So if J goes up, then your left side increases. Okay, actually the problem is I only considered for this proof, not the small example. I only considered the case where 0 to some things are all in the basement rather than shuffling of happens. So for small, so I put this x to be minimum of G1. And in the first case, I said this one is what is it? N0 and 1, something like that. So it's like a N R minus 3, R minus 2 up to this one. In this case, I did, but in the other case, when x is smaller than this one, instead of considering 20, I tried with this x, and then I could get satisfying result. But these are all for small examples rather than this general case. Okay. This is Dan.
Thank you.